Good morning to all. Myself, MYNAVATHI, Assistant Professor, Department of Mathematics, KSR College of Arts and Science for Women. My paper name is Complex Analysis. Next, Unit 3, 4, 5 topics are covered. The following topics are Unit 3, 4, 5 topics. Series, convergence of sequence, convergence of series, Taylor series, proof of Taylor's theorem, examples, Lorentz series, proof of Lorentz theorems and their examples. What is meant by series? A series is convergent if the sequence of partial sums approaches a limit. What is sequence? Sequence is a convergent if the terms get closer and closer to a specific number. Here, some more information about convergence of sequence and series. Convergence of sequence. A sequence is convergent if the limit of the sequence is a number. To determine if a sequence is convergent, you can find a formula for the nth term of a sequence and then find the limit of the formula as n approaches infinity. Convergence of series. A series is convergent if the partial sums of the series get closer and closer to given number. If a series is convergent, the number it approaches is called the sum of the series. A series, what is divergence? A series is not a convergent, is said to be divergent. What is a Taylor series? Taylor series is the polynomial or a function of a infinite sum of the terms. Each successive terms will have a larger exponent or a higher degree than the preceding term. What is meant by Lorentz series? Lorentz series expansion is considered to be an essential tool in complex analysis. Lorentz series helps us to work around the singularities of a complex function, and this as discussed the definition, formula, difference between the Taylor series and the Lorentz series with the solved examples in detailed. Next, I will discuss Unit 4. The following topics are covered in Unit 4. Residues and poles, isolated singular points, residues, Cauchy's residues theorem, residues at infinity, the three types of isolated singularity points, residues at poles, examples, zeros of analytic functions, zeros and poles. What is meant by poles and residues? Poles and residues are concepts in complex analysis that are used to find the value of a function over a loop. What is meant by poles? The points at which a function is not analytic. What is residues? The value of a function at a pole calculated by evaluating a non-polar part of a function at the pole. Now we discuss isolated singular point. In complex analysis, an isolated singular point is a point where a function is not analytic but is analytic in every other point in a certain neighborhood. In other words, an isolated singular point is a point where a function has no other singularities nearby. There are three types of isolated singularities: removable singularities, poles, essential singularity. The classification of an isolated singularity depends on the coefficients of a function's Lorentz series expansions at the singular point. A zero of an analytic function is a point in the domain of a function where the function's value is 0. In other words, a 0 is a function of f of z, which is a function f of z is equal to 0. Isolated singularity. Zeros of an analytic function are isolated, meaning they are not closer to each other. What is residue theorem? The residue theorem is used to calculate the integral of a function over a loop by identifying the poles of a function, calculating the residue at each pole, and checking that the poles are simple. Next, we will discuss Unit 5. The following topics are covered in Unit 5. Mapping by elementary functions, linear transformation. The transformation omega is equal to 1 by z. Mapping 1 by z is a linear fractional transformation and implicit form, conformal mapping, scale factor, local inverse. What is a linear transformation? A linear transformation is also known as the linear operator or map. Some examples of linear transformation include projections, reflection, rotation, and transformation. A linear fractional transformation. A linear fractional transformation is a type of linear transformation that is a composition of translation, rotation, inversion. It can be expressed as f of z is equal to a z plus b divided by c z plus d, where the numerator and denominator are linear. Linear fractional transformation are also called a Mobius transformation or bilinear transformation. Conformal mapping. A conformal mapping is a technique in a complex analysis that transforms a curve or a point on a plane while preserving the angles of the curve. It is used to solve equations for fields that can be represented by a potential function, such as conservation fields. Definition. A conformal mapping is a function that preserves the angles between curves in both magnitude and sense. What is the application of conformal mapping? Conformal mapping has many applications in different physical situations. Relation to harmonic function. If a function is a harmonic, then the transformation of such a function's conformal mapping is also a harmonic. Thank you.